So, Unit 2 talks more about the history portion of the atom. And again, you should be making your way through the homework as you see. I believe this is where we left off last time, where we looked at a cross-section of gold foil atoms and are seeing the alpha particles being deflected off course and sometimes even backwards. Now, this is what Rutherford saw, which again leads us to the question, okay, now what? Because that's usually how something happens, where we have these things where we have, okay, Rutherford did the gold foil experiment to disprove the J.J. Thomson's model of the atom. J.J. Thomson's model of the atom said that it should be a big mesh of positive charge with the electrons randomly spread throughout. Rutherford didn't like that idea, used alpha particles, and alpha particles have a positive charge, and according to physics, like charges repel, and therefore, he says, because of what these did, being marked off course, that the neutron had to contain something positive. It's the only thing that it could have ran into that would have deflected it. The fact that it went straight through also proved Rutherford's theory that Thomson was wrong. So, big ideas. Every atom is extremely small. Okay, we got that. But it has a dense nucleus in the center. That is where the positive charge is at. Or that's where it's concentrated. And it is those kind of big things that disprove Thomson's model of the atom. Now, the big thing that really starts to bother people is the rest of the atom is essentially empty space. And Rutherford then says that's pretty much where the electrons are located, in that empty space. If we recall back to an earlier lecture, we would remember that the electron is very small when it comes to the size and mass of the electron. And the proton is 2,000 times bigger than that of the electron, which means it is much more massive. Now, that crazy weird symboling that we have here, this looks like a Stargate A or something like that, is actually the measurement angstroms. And angstrom is just another way to say meters or nanometers, because the scientific notation gets to be so big for atoms, we had to come up with another way of measuring it so that our brains understand it. Just like for large distances, we come up with a light year because it's the distance that light can travel in a year. And it's that we use that because, again, that distance is so much larger than our brains can understand that we use a small light year. The number becomes smaller, easier for us to understand it. Rutherford then gives us, again, the nuclear model of the atom because it has a nucleus. The last and final subatomic particle to be discovered is done by James Chadwick. I like the term that we say that he confirmed the existence of yet another subatomic particle. Confirmed, because that means there were people that were going, there's got to be something there. The mass just doesn't add up. They could account for the mass of the proton because the number of electrons should equal the number of protons. And the mass did not match up to the calculations, allowing scientists to go, I think there's something else there. Now, why does the neutron, the last one to be discovered? It has no charge. If we're using electricity to find these things, something that has no charge to it can't be discovered using electricity. We have to figure out other means or methods to do it. It has a mass similar to that of a proton, slightly larger than that. Now, these are the big three of the subatomic particles. There are others. We do not get into them because I think understanding these and how they interact and why they do what they do with what we move on is more important than trying to just have you memorize the other subatomic particles. If you want to get to know them and know how they work, continue on and do bigger and better things. But I think understanding these and how they interact and what they do to drive the chemistry that we will be studying the rest of the year is important. And this doesn't happen until 1932. The neutron is confirmed. You're looking almost 20 years that this is all of a sudden going, all right, so neutron, right? Yeah. But not everybody, believes in it because it hasn't actually been discovered. So, did everyone buy into this idea or technology that they're moving forward with? The answer is no, because it goes against all the fundamental laws of nature. Physics was if it doesn't work at large scale, it doesn't work at small scale. That was the going theory. The bigs of physicists of the times had a problem with these physicists that were going and trying to do research on the atom. They would always say, well, that can't be right. It doesn't follow the fundamental laws that we know to be true. Like charges repel, opposites attract. If you are telling me that electrons orbit, hang around the positively charged nucleus, why does the atom not collapse upon itself? if you have more than one proton in an atom, how does that nucleus stay intact? If you have two, it should completely rip itself apart. Because like charges repel. How are you able to get, for an atom, say palladium, 46 protons in a small area that you're suggesting? How do you have such positive charge and have 46 electrons in that area around it and not collapse upon itself? The fundamental laws of physics, the Newtonian laws of physics, don't allow for the atom to truly exist the way we know it does. They had to develop new laws, a new way of understanding the world. And it never is smooth sailing. They have now what's called quantum mechanics. Because in the quantum world, you don't get to like make yourself bigger like Ant-Man, okay? And who knows if you were able to kind of bridge time and space in the quantum world. Who knows? Who knows? But the thing is, we had to develop new ways of understanding how things worked. That's what quantum mechanics became. And it was the young physicists that pushed this new area to a beginning in the early 1900s. So when we talk about the atom and how long we've known about the atom, 100 years, we're coming up on, 100 years of knowing about the neutron. Still haven't known about that for 100 years yet. Which we think is like, but we've been studying this thing for how long? Quite some time. But it's not even that old yet. It's still actually very new. And we're still finding things out. So, to understand at least some of the quantum mechanics that we are going to cover, we need to talk about some other things, and that's called electromagnetic radiation, better referred to as light. The distance between corresponding points is known as a wavelength. It looks like an upside down Y, it's kind of a weird looking H. It is the Greek letter lambda. The amplitude, which you can adjust using an amp, is the wave's height from the 0 point to the crest or to the trough. An amp, such for a car or a home, would amplify, make it louder usually. The frequency, which looks like a V, and ultimately that's what it is. It's actually supposed to have some more fancy curve on it, is for the Greek letter nu. It is the number of wave cycles that pass a given point per unit of time. The unit of cycles per second is known as the hertz. But it's not going to, go pick you up because that's Enterprise. Cha. Yeah. So, this looks like it didn't convert over. The wavelength should be written as that. So here you have an equation for the speed of light as a constant, which, by the way, is roughly 300 million meters per second. Now, that is all light. All electromagnetic radiation moves at the speed of light. The wavelength changes. The frequency in which those wavelengths also change. And it is that direct correlation between wavelength and frequency that allow for that to happen, because the speed of light is constant, never changes. So, what does an electromagnetic spectrum look like? Well, there you have it. All visible light is between 400 and about 750 nanometers. How do scientists tell what's in, say, a star, or what a star is made of, is dependent upon what's called the line spectrum. The line spectrum is the bottom. It's the fingerprint for every element on the periodic table. Every element on the periodic table has a unique line spectrum that tells us what it is, because it is unique. Now, we are going to eventually talk about, but those lines, again, are at certain wavelengths. Because they move at the speed of light, you could tell the frequency. The frequency allows us to understand the energy that those lines have associated with them. You can see some of these lines if you have a kind of a spectrometer, where you look at different light bulbs. Different light bulbs have different line spectrum as well. An incandescent light bulb usually is going to have very much visible light, but a like a halogen lights are going to have a different, they're going to have more of a line spectrum, because they have different compounds in them creating that light. That's why the sun makes a rainbow. It has all of them, and that's just because of the prism scattering out. Okay? There are other wavelengths. You can see that short wavelengths are going to be your UV light, ultraviolet light, the purple stuff. The infrared, not as energy, because the wavelengths are longer. Okay? You don't get burned in the summertime by infrared light. You get burned in the summertime by the UV light, ultraviolet light. Now, some of us look at this and might go, hey, this is backwards. In a way, it is. Normally, we think of the color spectrum as Roy G. Biv. Red, orange, yellow, green, indigo, violet. Blue, indigo, violet. Okay? Those are what we have. Now, the wave nature of light doesn't explain why we see things glowing when they get hot. Say it is a hot iron or wood when it's just kind of smoldering. Okay? Those little glows that we see. Okay? The wave nature does not explain those. Okay? There's something else going on there that we won't discuss at this time.